This example comes out of 4.1, increasing and decreasing functions. So here we're asked to find the intervals of increase and decrease for f of x equals 13 minus 8x plus 6x squared. Because it's a relatively simple function, which just turns out to be a parabola, you could probably do this without calculus. If you had a graphing calculator, just look at it and say, oh, when does this thing go down, when does it go up? With calculus, I think it's actually even easier. If we take the derivative, this derivative is negative 8 plus 12x, or if you prefer 12x minus 8. Critical numbers for that derivative, in other words, is it ever 0 or undefined? Well, there's only one spot, and that's where 12x minus 8 equals 0. So 12x equals 8, so x equals 8 over 12, or 2/3. So there's one place here at 2/3 where this would have a horizontal tangent line, which makes sense given it's a parabola. If you draw yourself a little picture of it, it makes sense that there's going to be one spot there that isn't increasing or decreasing. Now, I just need to check on the left and on the right. So if I take a number less than 2/3, like 0, I'll see that this thing is, first derivative is negative. And if I pick a number greater than 2/3, like 1 or 10 or a million, I'll find out that this is positive, which agrees with even the rough sketch that I did up above there that says this function, f of x decreases on the interval from negative infinity to 2/3 and increases on the interval from 2/3 to infinity. Next one looks much more complicated, but still just a polynomial, so it's actually not too bad, especially because it's kind of a artificially designed one that gives us nice round numbers. But we'll start off the same way. If we want to know the intervals of increase-decrease, my first thought is take the derivative. The derivative of this, 4x cubed minus 12x squared minus 40x. If I look at that a little closer, I can see that it factors quite nicely. It gives me 4x times x minus 5 times x plus 2. The reason why it's useful to have it factors is because I can look at that and say, oh, well, I can see that the only places where this might change directions, where it might be 0, is at 0, at negative 2, and at 5. This derivative equals 0. There's nowhere where this derivative is undefined, so those are my only critical numbers here. And now I just look to see when is it positive, when is it negative. So if I pick a number to the left of negative 2, negative 10 million, I'm going to have a negative times negative times negative, which tells me that this thing is decreasing. So the function is decreasing on the interval negative infinity to negative 2. Pick a number in between, like negative 1, and I'll have a negative times a positive, and so my function is increasing on this interval from negative 2 to 0. Not increasing or decreasing at negative 2 or at 0. Now try a number between 0 and 5, and I'll have positive, a negative, and a positive, and this thing is decreasing again, so it's also decreasing from 0 to 5. And finally pick a number greater than 5, and I'm going to have positive, 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 which means this thing is increasing, and so from 5 to infinity I have an interval of increase. Be a little bit careful of, I've seen students once in a while who automatically, they find one interval that's negative, for instance, like this first one here, and then they assume it's going to go negative, positive, negative, positive, negative. It's not always the case. Depends on what your roots, your zeros are. So it is worth, doing the analysis the way we have been, just checking it out before you just make assumptions. So, but not too hard a question if you just find the first derivative and find out where is it positive, where is it negative.